Hello and welcome to this tutorial. In today's tutorial, I'll talk about the bisection method. The bisection method is a method of finding the root of an equation of the form f of x is equals to 0, where f of x can be an algebraic equation or a transcendental equation. Now, when using the bisection method, we shall start with the use of intermediate value property to search the root of the equation. Basically, the intermediate value property basically gives the interval where we can locate the root of an equation. The intermediate value property simply says that given an equation of this form, then if for a certain interval a comma b, where a and b are real numbers, if f of a multiplied by f of b is negative, then there exists at least one root of the equation f of x is equals to 0 in the open interval a comma b. What this simply says is that if we're drawing a graph, for example, we know that the root of an equation f of x, when we draw the equation y is equals to f of x, we know that the root of the equation f of x is equals to 0 will be the point where y is 0, that is this value here, the value of x at this point. So this means that if we locate some point a here and some point b on this other side, such that f of a is negative and f of b is positive, this is f of b and this is f of a, so that f of a is negative, f of b is positive, then it will mean that f of a times f of b will be negative. And also we have a second case where if the curve is of the form this, then we locate a somewhere here and b somewhere here, then we see that in this case f of b will be negative and f of a is positive. So again, f of a times f of b is negative, is less than 0. So in this case, the intermediate value property simply says that if we can locate an interval where the curve crosses the x-axis, that is, if we can find some points a and b such that the curve crosses the x-axis between a and b, then the intermediate value property says that there exists at least one root of the equation f of x is equals to 0. So in this, when using the intermediate value property, or rather when using the bisection method to find the root of a given equation f of x is equals to 0, we shall start by intermediate value property to search for such an interval a and b, to search for values of a and b such that the curve crosses the x-axis. So we simply need to have either f of a being positive and f of b being negative, or we find the case where f of a is negative and f of b is positive. So if we can find that such values of a and b, then we are going to determine that the root lies between a and b. There exists at least one root between a and b. Once we determine the interval where we expect to find the root, we apply the bisection method. We consider the interval now, the interval a and b. What the bisection method will do is simply to partition this interval by finding a value c such that c is equals to a plus b divided by 2. So the bisection method simply partitions the given interval into two equal sections. So once we do that, once we find the value of c, which is the midpoint of the interval, then we have two intervals, the interval between a and c and the interval between c and b. So the problem now again is to apply the intermediate value property to find out whether the root lie between a and c or between c and b, simply by checking the same condition as we did here. If the value of a is positive, the value of the function at point a is positive, and the value of the function at point c is negative, then we are going to conclude by the intermediate value property that there exists at least one root between a and b. However, if the value of the function at point a is positive and the value of the function at point c is also positive, then the intermediate value property does not give us information about whether there exists a root between a and c. So in such a case, if that happens, then we shall check whether the function changes value as we move from c to b. If we find that the function changes value as we move from c to b, then we shall conclude by the intermediate value property that the root lies between c and b. So we're going to apply to make use of an example and see how we can apply this method. So we want to find the root of the equation e raised to power x minus 5x minus 7 is equals to 0. Now we are going to start by searching the interval where we expect to find the root of this equation by applying the intermediate value property. So we say that our function here is e raised to power x minus 5x minus 7, and we are going to look for the positive root. So we can start by finding f of 0, and this will be e raised to power 0 minus 5 times 0 minus 7. So we say that e raised to power 0 is 1, so we have 1 minus 0 minus 7, that will give us minus 6. Then we find f of 1, which is e raised to power 1 minus 5 times 1 minus 7. And if we work out this value, we get minus 9.28, approximately, correct 2 decimal places. So by computing the product f of 0 times f of 1, we get this is minus 6 times minus 9.28, and definitely this value is positive. So by intermediate value property, we see that the intermediate value property does not give us information whether there exists any root between 0 and 1. So we check the value of the function at 2. So in this case, we get e raised to power 2 minus 5 times 2 minus 7. And if we work out this, we get minus 9.61. Again, the function is still negative. We say f of 0 is negative, f of 1 is negative, f of 2 is negative. So we are looking for the point where the function will cross the x-axis. So we continue doing this until we find a positive value. So in this case, we can find f of 3, which is e raised to power 3 minus 5 times 3 minus 7, and this will give us minus 1.915. Again, the value is still negative. So we find f of 4, we get e raised to power 4 minus 5 times 4 minus 7. And if we work out this, we get a value of around 27 7.6. So that the value is positive. So clearly, we see that when we multiply f of 3 by f of 4, we shall be multiplying a negative value, negative 1.9, by a positive value, 27.6, so that the value we get will be negative, less than 0. So this will imply, if we apply the intermediate value property, that there exists at least one root of the equation on the open interval 3, 4. So this is the root that we want to find. So how do we get this root? At this point now we apply the bisection method. So we have the value 4, or rather 3, and then 4 here. We have 3 and then 4. We can call this point A and then this B. So A is equals to 3, B is 4. So we want to partition this interval by the use of bisection method by finding a value C such that C is equals to A plus B divided by 2, the midpoint of this interval. So this will be 3 plus 4 divided by 2, which is 3.5. So we have the value 3.5 there, which is the value of C. So the problem now is to apply the intermediate value property to see that, to check whether the root lies between A and C or between C and B. So in this case, we see that we had obtained f of A, which is equals to f of 3, and the value was negative 1.915. The value was negative here. So the problem now, we need to find f of C, which is f of 3.5, and this will give us e raised to power 3.5 minus 5 times 3.5 minus 7. And if we work out this, we will get a value of the value of f of C will be around 8.6, which is a positive value. So that f of A times f of C is equals to negative 1.9 approximately, multiplying 8.6. And because we are multiplying a negative value by a positive value, we are going to get a negative number. So in this case, the value is less than 0. So by intermediate value property, we see that there exists at least one root between A and C. So in this case, we are going to discard now the interval C and C to B, and we are now left with the interval AC. So our interval, we shall now have, we initially had A and B, but we have partitioned this to have the C. We have seen that the root lies between A and C, this interval here. This interval. So we are going to discard this interval. So we are going to move a B here, and we repeat the process. So that now A was 3, B was 4, and C is 3.5. So what we are going to do is that we're going to move this B to the point C, so that we now have the interval A, B, but A is still 3, but B is now 3.5. phi. So again, we partition the interval by finding c. So we write c is equals to a plus b divided by 2. And this is 3 plus 3.5 divided by 2. And we can get 3.25. So then we repeat this process. We can repeat this process many times until we have a very good approximation to the root of this equation. So to implement this method, we are going to use the MATLAB, and we look at how we can use MATLAB to implement these steps. So notice that the method starts by searching the interval where the root lies. We apply the intermediate value property. Once we get the interval, we use the bisection method to partition that interval. Then we go back to the intermediate value property to check which interval the root lies, whether this interval between A and C or between C and B. Once we identify the interval, again we partition the identified interval by using the bisection method, and then we go back to the intermediate value property. So how do we implement this in MATLAB? So we are going to start with the variable. We have the variable x, or the symbol x in MATLAB session. Then we write the function. Our function is e raised to power x. So this is expressed as exponential x, then minus 5 times x. The multiplication, we use the asterisk, remember? Then minus 7. And then we want to search the interval. We will start with we'll start by setting the counter. I is 0. Sorry, I is equals to 1. Then we want to start with x naught, or x is equals to 0, and then compute the value of the function at that point. So we write xi is equals to 0, because we want to start at 0 as we have done here. We have started by computing f of 0. F of 0, we got negative 6. Then we obtained f of 1, we got that. F of 2, we want to follow the same procedure. So we write f of xn, I is equals to 0, I is 1, I is the counter. Then we can say now, while f of x and I is negative, is less than 0, we increase xn. So we write xni plus 1 is equals to xni plus 1. So this will work out. First, this computes the quantity, the function here computes f of x at when x is 0. So that should give us negative 6, which is less than 0. And so xn is increased from 0 to 1, and then computes the value of that, the function at that point at x is equals to 1, which will give us a value of around negative 6 point something also, negative, as we obtained here, which was negative, this was negative 9.28. And then because the value is still negative, the value of xn is increased again by 1. So this is repeated until a positive value is obtained, because the loop is supposed to stop when the condition is false. So we need to increase I to I plus 1 also. Then we add the root. And then, now once we obtain the values of, once the loop ends, notice that xn should increase from 0 to 1 to 3. Sorry, from 0 to 1 to 2 to 3, 4, and so on, until when the value of the function at that point is positive. So once that is determined, then we can set the value of a and b. B we shall set it as the value xn I and a as xn I minus 1. So that if xn increased from 0 to 1 to 2 to 3 up to 4, or like let's use the values that we have here. See that when we were doing this, x increased. We started with x is 0, then x is 1, x is 2, x is 3, up to x is 4. Then, because we went up to x is equals to 4, that's when the value became positive, the value of the function became positive. Then we assigned b to a value of 4 and a value of 3. So we want to do the same. This is xni and this is xni minus 1. So we want to assign the same value as we assigned here. A is equals to 3, b is 4. So once we do that, then we can set another counter. I will call it j is equals to 1. Then we'll now apply the bisection method. So I'll say while the absolute value of a minus b is greater than some value 0.00005, I want the root correct to 4 decimal places. These are zeros, 0, 0, 0, 5. So because I want the root correct to 4 decimal places, sorry, then the root will just be the difference between the error, rather will be just the difference between the root a minus b. So a minus b less than that. When the absolute, as long as the absolute value of a minus b is still greater than this, I need to do the next iteration until when the value of a minus b, that is, when the interval is small enough. Remember, we are partitioning the interval a, b by finding c. So if the interval is small enough, then the value of c I will get to be a very good approximation to the root. But as long as the interval is large, then the value of c will not be a very good approximation. So I want to make the interval very small between a and b, then I pick a value c. So this will be the stopping criteria. Then I'll compute xk, which is now my root, j, which I'll write as a plus b divided by 2. This is the use of bisection, so that when I determine the value of a, the value of b, then I compute the root a plus b divided by 2. Now, here, if the computed value here, the value of the function at xk, evaluated at this point, the value we have obtained here in this step, if the value of the function evaluated at that point is equals to 0, so we use equals for the logical check. If the value is 0, then we have obtained the correct root. So I'll need to break. So that statement should terminate the iteration. Otherwise, if it is non-zero, then I'll need to partition the interval further. So I'll check I'll now apply the intermediate value property. So I'll write else if f of x k evaluated at j times f of a. Remember that f of x k j now is what we were calling c when we were doing when we computed up there. C is equals to a plus b divided by 2. So if this quantity is negative, then the root lies between a and xkj. So I need to set b. I need to set b to be equals to, so I'll set b to be equals to xkj. Otherwise, if the interval, if this quantity is not negative, then the root does not lie in this interval. So I need to set, so I'll say else, that is, if this quantity is not negative, then the root does not lie in this interval. So I'll need to set a to be xkj. And then I increase the counter. J is equals to j plus 1. So notice what we are saying here, like we had said earlier here, that if we identify that the root lies between a and c, then we discard this interval. We move b to c, so that our b now becomes 3.5. However, if we had identified that the root does not lie between a and c, then we need to discard that interval. So we move a to c, and we are left with the interval c, b, so that our a becomes c here. So it is either the root is in this interval between a and c, and we move b here, or the root is not in this interval, so it is in this other one. So we move a from this point to this point. So we move a from that point to point C. So that is what we are saying here, that if f of x, k, j, which is our C in that case, times f of a is negative, then it means that the root lies between a and c. So the value b is moved to c. But if that is not the case, then a moves to c, so that the root lies between c and b, so that we replace c by a. So now I'll need to add my iteration there, and also add the while loop at that point. I can print my output. So you're saying the fprintf function. So I can write f of x. So here I will put a placeholder. The percentage is a placeholder. I can write the value of x correct to 5 decimal places. So I can write 0.5f is equals to, then I'll write, I'll put another placeholder, 0, or rather percent 0.5f. Sorry, this is not correct. I should just write, we're getting the root. So I'll just write the root is, then I'll put the placeholder 0.5 f. I want to output the result as a floating point decimal, correct to 5 decimal places. So I'll put xk j minus 1. The reason why I write j minus 1 is because after computing xk at this point, xkj at this point, before that iteration is over, j has increased by 1 to j plus 1. So in order to get what I had there, then I need to subtract this 1 that has been added here. So that I write j minus 1. So learning this should give us the output. I'll do this in MATLAB. So I have the code here, and I want to see before we look at the solution here, the final solution. I want to look at the first part here. So we create a symbol in MATLAB session, then the function, then the counter, xi is 0. We compute the value of the function here, and then I want to print the output so that we can see the values. So I use the fprintf to print the output at that point. Then we increase the xn. So if f of xn is less than 0, then we increase xn. So we start from 0, then we increase to 1, then we increase to 2, and so on and so on. So I want to learn this so that we can see the output here before we put the other part. So we say f of 0 is equals to minus 6, f of 1 is minus 9.2817, f of 2 is minus 9.6, f of 3 is minus 1.9145, and f of 4 is that, just like we had obtained here. Just like we had obtained here, f of 0 was minus 6, then f of 1 minus 9, f of 2, f of 3 up to f of 4, which is 27.6. So we have those values. Yeah, so this one generates those values and then stops at a point when xn. You can see xn here. If I type xn has increased from 0 to 1, 2, 3, up to 4. So the idea is to set a is equals to 3 and b is equals to 4. So when we write, when I put the other section here, now I'll be putting a is equals to xn minus 1. See that xn minus 1 should be xn I minus 1 should give us a value of 3. I want to learn that one here so that we say the value is 3, and xni should give us the last value here, which is 4, so that we see that we have set the values correctly. Then we set another counter, and then the stopping criteria for our root. Then xj, this is now the iteration, xkj is equals to a plus b divided by 2. This is the bisection. Then we say if xkj is 0, then the correct root has been obtained, so we stop at that. If that is not the case, then we check, we apply the intermediate value property to check whether the root lies between a and our root, the value that we have computed here. And if that is the case, we set b to be xkj. If it is not the case, then a is set to be xkj. Then we increase j by 1, our counter. Then we add and we print. The root is given by x is equals to that, j minus 1. I've added another statement here because I want to know how many iterations did we perform. So when I run this one, I'll get the root. I'll see that the root is given by 3.11734, and this is after doing 6 iterations. So now this method can be applied even if we have a different equation. Suppose I write the function here. You see this function was e raised to power x minus 5x minus 7. So suppose I put this one as x squared. So for this function, the root lies between 3 and 4. But suppose we change this from 5x to 5x squared and learn, so that we have now a different function. We see that f of 4 is still negative now, but f of 5 is positive, so it means that the root lies between 4 and 5. Then the iterations are carried out, and we can see the final value. The root is given by 4.80930, and this is obtained after 10 iterations. So this method now, this code now determines the number of intervals because we have put the stopping criteria as the maximum error that we are going to allow here. So basically, this is how we can implement the bisection method in MATLAB.